Well, hi everyone. Today we're going to actually go old school in that we're going to run some analyses, but not with the GUI. We're going to do it through the functions that are contained within the R package. So what I'm going to do first up is load up RStudio and just talk about a few things before we get going. But even before I do that, let me change the working directory because I'll forget to do this later on. So that just will let me access the data that I have available. Okay, so what we have, ignore all that, what we have are a bunch of data sets that we have available on our website that's there for you to download and to play with. And what I've done is I've downloaded that data into my session here, and we have 4 files. The first contains the mark information, the second is the map, the third contains the phenotypic information, and the fourth contains the R commands that we're going to be running through today in today's session. So let me show you a little bit. Well, let me give you a hint of what's contained in each of the files. Hopefully they're pretty obvious. So the first one's a peeling ped file. It contains all the marker data. The first 7 columns are standard peeling, like they're mandatory for a peeling ped file, but Eagle ignores them. So they can actually be anything you want. The thing that matters to Eagle most is where the SNP information is contained. Okay, so the phenotypic file, the first row has to contain column headings. That's the opposite of the marker genotype file. So whether you have a peeling ped file or straight ASCII text file, don't put column headings in there because that's just going to cause Eagle havoc. But certainly with the phenotypic file, you need, it makes sense to have column headings there. Otherwise, when it comes to analysing the data, it's not going to make any sense. And then let's just look at the last file just quickly, the map file. Nothing very exciting. All we have are the SNP name, the chromosome, and the position. So Eagle does do its best to try and pick up errors. It can't pick up everything, but some things it will check for is to make sure that the number of markers that you have in the map file matches the number of columns that you have in your genotype file, and also the number of rows that you have in your phenotypic file matches the number of rows that you have in your genotype file. So I'll do things like that, but it can't do everything. So one of the things is the ordering that you have your SNPs in. This is the ordering it assumes the columns are in. Okay, so let's go back to console and let's just load in that map, the R script. Okay, so what I've done is, because I can't type and talk at the same time, I've actually just written out the commands we're going to run through, and we can run through them pretty quickly. I'll just talk a little bit about what's going on with each. So let's just load in the Eagle package. There we go. You know it's loaded successfully because it has this little bit of heading here. But let's load in the marker data first. So the command itself, if you're stuck and you want to have a look at what is going on, we actually have quite detailed help pages. So for read marker, there's a whole lot of information contained here about the the form, what's going on here. There's actually a fair bit going on with this read marker. The reason behind that is when we designed Eagle, we wanted it to be able to run on systems where the marker data may be much larger than the memory capacity of the machine. The only way we could do that was by actually not reading the data into memory. What we do with this command is we actually reformat the data into a form that can be read from disk very quickly. So this command can take a bit of time. If you've got a file that's just enormous, so half a terabyte in size or something, then this is going to take quite a bit of time to run through. But the good thing is it can handle data of any size. So the other thing with this command also is it can handle data of 2 different formats. It can handle either peeling ped files, which is a well-known format, or it can just handle straight ASCII text files. And as I said before, the main thing is make sure you don't put column headings in because that's just naughty. Okay, So let's just run this command. It's not going to be very exciting because it's so small. It just runs through very quickly. And like there's some summary information given here, probably stuff that you'll never look at unless something goes wrong. But it is a good habit to get into of looking at two things. First of all, make sure that the number of individuals you have being read in matches up with what you know to be true, and also the number of loci that you have. They're two very important bits that can save you a lot of grief later on. But other than that, you can probably ignore everything else. Okay, so let's read in the phenotypic data. Again, if you are interested in all the lovely help pages we have on this, then there's a whole lot of information contained here about some of the nuances behind the phenotypic data file. But it's just like read table, except we're doing a lot of other checks underneath the hood here. So it's not just straight read table. We want to do a lot of checks along the way as well. But in essence, what you end up with is an object that is a data frame. So if I go class P, sorry, I need to read in first. Let me read it in. Go class P, then you see it's a data frame, and you can do with it everything you'd normally do with a data frame. So there you are. Okay, so the last command that we have in terms of reading in the data is the map file, and the map file is optional. Like, you can do GWAS without having a map file. What it means though is when it comes to interpreting results, that makes it a little bit difficult, but you can do it. But here we've got our map file, so we'll just read it in, and again it reads it in as a data frame. So if I look at the class, there it is, and here are the names. Okay, so there we go, and that's how easy it is to read in the data. Just 3 function calls to read in your market data, your phenotypic data, and a map file if you have it available to you. Okay, so now we get down to the good stuff, and this is where we come along and perform multi-locus genome-wide association mapping of your data. And the function that does this is called AM, for association mapping. And if we look at the arguments of AM, there's a few of them. It's a fairly versatile function, but the core ones are, you have to put in, like, you have to tell Eagle what the trait is, because the phenotypic data file can potentially contain a bunch of traits that you might want to analyze. You need to specify what the form is for your fixed effect part of the model, and you can just use all your linear model type of nomenclature here to specify any sort of model you like, and then you need to tell Eagle where the genotype data is, where the phenotype data is, and where the map file is. Other than that, there's not too much about, like, there's not much else about this function you need to adjust, except one really important thing that sits right at the end of this command, and this is this gamma value. So a little bit of background. Eagle approaches association mapping as a model selection problem, and it goes about trying to identify the best model by using what's called an extended BIC. So those of you who are familiar with a BIC, then extended BIC is just an extension of that, but it comes along with this regularization parameter gamma that controls how conservative that extended BIC is going to be. The gamma value ranges between 0 and 1. And for those, like, if you want to do an analysis where it's very conservative or most conservative, you leave that gamma value set at 1. If you want an analysis where it's very anti-conservative, then you have values that are close to 0. So obviously, in real life you don't know what that value is, and we'll talk a little bit in a moment about how to deal with that. But as a first step, and as a preliminary analysis, and as the fastest way of analysing your data, leave that gamma value set at 1. So set at 1 by default, so you don't actually need to specify it formally in the function command, and you can just run this command as it is, and what it will do is it will start giving you the output for analysis. So it's just running like it's an iterative process. It's building the model up step by step, and what we have here as a final result is it has found 2 regions of interest. They are located on chromosome 20 and chromosome 19. One of the other things that you can do once you've run this analysis is actually just have a nicer summary of the results. So if you go or use the function summary AM, then what that allows you to do is gives you all the information that we had before and then some. So it also tells you the significance of the effects and the sizes, and also it gives you the amount of variation the SNP explain. So just a bit more information there. Okay, so that's a preliminary analysis of the data, but in most cases people are going to want to analyze the data where you're doing it under a known false positive rate. So what we've done is, suppose we're actually interested in redoing that analysis, but now where the false positive rate is controlled or kept to 5%, then what we've done is we've actually written a function that will find that value, will find that gamma value corresponding to that 5% false positive rate for the model that you specified. So it's model specific. If you change your model, the gamma value will change and you need to redo this. But what we're doing here underneath the hood is we're using permutation. Unfortunately, there's no analytical way of finding the relationship between the gamma value and the false positive rate, so we have to do it empirically. But what we've come up with is I think it's a fairly clever way of doing it, in that even though we're performing a large number of iterations here, or replicates, that doesn't mean it takes a long time. So we've found in practice it probably takes about five to 6 times longer to run this function and do these steps than if you knew the gamma value in advance, but it's not a huge costing to this. So what we'll do is we'll actually, so everything else is the same. You're running the same trait for the same model with the same data, but we're just setting the false positive rate to be 0.05. It's going to take a little bit of time, because the default value for this is to perform 100 replicates. So what it will do is it's fairly fast because the data is quite small, but it's just going to come along and calculate the gamma value that will give a false positive rate of 5% based upon 100 replicates of the data. If you've got the time and the energy, the more replicates you do, then the more accurate result you get. But the final result that you get here is 0.894. The other thing that we do also is we actually produce a table of gamma and false positive rates. So it comes at no additional cost computationally to look at other gamma values and false positive rates, and here's a table of other values. So if you change your mind and want to do an analysis at, say, the 10% level instead of the 5%, then what you would do is maybe you'd pick 0.73 as your gamma value, and so on. So you just go along the analysis that way. Okay, so now that we have this false positive rate, let me just show you what sits within that structure. So the answer that you get from this false positive rate for AM is just a list structure. There's a bunch of stuff that sits in there, but the thing that matters most is this set gamma, because that contains the value, the gamma value corresponding to the false positive rate that you specified. So all we do is we just repeat the same analysis that we had before, except now what we're doing is we're specifying the gamma. So where before we left the gamma value at its default value of 1, we're now going to perform the same analysis, but with the gamma value fine-tuned to give a false positive rate of 5%. So let's do that, and it will be, again, very fast. Okay, interestingly enough, the same results as before. And in most cases that's not going to be the case. It's because this is such a small toy data set and it's simulated, so things are all a bit artificial. But in most cases, especially for the larger data sets, so what we've found in practice is when you have data sets that say have 500 more individuals, then setting the gamma value to being a gamma of 1 is very conservative. So the advantage of that is whatever results you get, are true, but the downside is in most cases you're probably missing important results. So what we did for the paper on this is we also reran that analysis where we had actually fine-tuned the gamma value for that false positive rate, and we found you're able to find a lot more results in that case. So in practice, you're probably almost always going to be doing this. Again, we'll just do a summary just for interest, and it's just going to be the same as before. There you go, and that's kind of the process you go through. So I'm hoping that's all pretty obvious and simple. As I say, we've put a lot of effort to try and make the package as simple as possible. By all means, send us feedback if you come along. And here's a little trick: if you go to library, comma, and then the name of the package, it gives you all the information that's contained in the description file for a package, some of which is the helpline. So we've actually set up Eagle Help at siro.au. That's our if you like, our help desk. So if you're really stuck and having problems, by all means, or if you find bugs, whatever, send us an email and we will do our best to try and solve the problem. Obviously, there's also the Eagle website that I'm assuming you're probably watching this video from. And other than that, I think that's pretty much it. So as I said, everything here is available for download. Thank you for your time. Have fun. Okay, bye.